of phenomena, then and then they will complain about this bluish line that you put in the samples, and this is how it happens. It's just dissolving the enamel when the acid goes in. Properties, because on the incisal third is critical to get this kind of effect. So this is an example of layering of composite, and you can really see the change when we are doing this polishing and this finishing. We can create this halo effects just by modifying the shape of the tooth. Okay, this is possible to do also with composite. We just need to try to copy what we see in nature. Okay, if we use the right materials, you just need to copy the anatomy, and that's it. So also another thing that has a big impact on the opacity, on the scattering, is the refractive index. Okay, the refractive index contrast. So basically, we'll talk about the refractive index a little bit. Refractive index is a measurement of how much the light changes direction when it moves from one medium to another. And this represents really the optical density of the material. So the more optical dense the material is, then the higher the refractive index is, which means the light travels a bit slower in this material. So as you can see, we have different materials with different refractive indexes. And those materials can be part of our systems, of course. And we were talking here about just simple materials. The reality is that we have much more complex materials, and we can see the classic effect of the spoon that is being broken, you know, is broken by the water here and the glass, but reality is just the light that is bending, but it's not really that the spoon is changed. So what is the refractive index of enamel, and what is the refractive index of dentin? Enamel has a refractive index of 1.62, dentin has a refractive index of 1.54, and our materials are relatively similar. So ceramic and composite both match pretty well the dentin refractive index, although they are a little bit smaller than the refractive index of the enamel. So there is some materials that can match the refractive index of the enamel, but is that really important or not? This is the question. Do we need really to match the refractive index of the enamel? So basically the effect of matching the refractive index won't be very, very visible, because the difference from, let's say, the minimum to the maximum is just 0.08. So this is not a big difference, okay? So we can only see very, very slight difference in the reflection on the surface. We need to understand the higher the refractive index of our material, the more it will reflect the light. And we will also see just a little bit of increased thickness of the halo effect. You know, the thickness of this whitish orange part in the incisal third, it will be a little bit thicker with a 1.62, but it's very subtle. It's very subtle, because 0.08 difference in refractive index will only really be extremely visible when we have very thick samples. So we will need something like 1 centimeter sample, and then we'll be able to see immediately a huge difference between both. But at the thickness that we're working, which is normally around 1 millimeter, it's very, very unlikely that we are going to see these differences unless we use really like super high magnification in order to see this. So the reality is that it's much more subtle. So the important thing about the refractive index is actually the contrast between them, okay? So we need to understand that all materials that we use are a combination of things. So let's try to understand this with a cloud, okay? Cloud is one of the simplest things that we can have. And if we look at the clouds here, we need to understand that the components are just two, which are very simple: water and air. And both components are transparent, but the cloud is not transparent. So yes, both components are transparent, but together make the cloud white and not very transparent. It's a translucent material. So the key is the difference between the refractive indexes. So this is how it works. Simple way, okay? We have the drops of water flying in the air, and then we have the light coming, and it's going to hit one drop of water, it's going to refract, change direction, and then when it reaches the other side of the drop, is going to refract again. So we will see a change in direction, then hits another drop and gets refracted again, and so on. So there is multiple refractions taking place, as well as other phenomena. Then at the end, it's a chaos. So the particle will start, the photon will start jumping around until eventually it goes out of the cloud, because it reached one of the drop that is really on the margin, on the outside, on the boundary, and then it goes out. So of course the light, this pattern and all this different scattering pattern will be completely different depending on the position where the photon is hitting the drop, and depending on the drop that it's hitting, and of course those drops are moving. So you need to understand that there is a chaos that takes place every time the light is coming from the sun in all the same direction, is going out of the cloud, forming a complete chaos of light. So it goes in all directions outside of the cloud. So this is basically the principle of scattering. And the more difference we have between these components, the more scattering of light we will have. As simple as that. So if we want to make a very opaque material, the only thing we need to do is just add particles that have a very high refractive index. Let's say this is an example. Of course, we are not really using a lot of zirconia in the composites, but just imagine that in ceramics we use a lot of zirconia powder in order to make it opaque. But this is the difference between the matrix and the particle. It's huge. So a very big contrast between both means that there will be a lot of chaos. There will be a lot of scattering here. So that will create much more opacity, okay? So just at the moment the light goes inside the material, it will be instant chaos of light. On the other side, if we want to make a very transparent material, what we do is just matching both refractive index. So we have the same refractive index in the particle and the matrix, and that's exactly the same, the same refractive index. So it means we don't see any limit, any boundary. The light will only be refracted once and will just go through the material, because the light won't see any difference between both components. So that's the ideal way to make a complete, like a glass, complete transparent material. No matter that the particle size is big or small, if we match the refractive index, the material will be transparent for sure. So that's the way to control with the refractive index. And finally, we have another one, which is also related. I mean, all of these are connected, but it is very important to understand the ratio between the components. So we need to understand that even the dentin and the enamel have the same composition, hydroxyapatite, organic material, and water. They are completely different optically just because the composition is completely different regarding the percentage. So we have a more heterogeneous material on the dentin. So we have like 45–50% mineral, while the enamel is almost like a pure mineral, 85% and more of hydroxyapatite. So what we need to understand is the more mineral content we have, the more transparent it becomes, because it's more like a pure mineral, all right? So this is actually what happens with the teeth when they become older. We have an aging process, and this aging process is actually going to increase the amount of mineral. So, and that's going to increase the transparency of the tissues over time. And this is very important to understand, because most of the time we've been only thinking about just handling color, just handling the chroma, okay, and working just with the chroma to get higher value, lower value, and so on, and talking only about pigments. But this is more about the opacity of the materials, okay? So let's see how it goes a little bit, and what's the structure in the enamel that makes it so special. Okay, the enamel rods are made, well, the first hierarchy is actually the crystallines of hydroxyapatite. So they are coming like packed with some proteins inside also, but it's basically crystallines of hydroxyapatite that are packed into the shape of the enamel rod, which is like this. Okay, it has a lot of bendings in the inner side and straight on the outer side. Then we have all these rods packing into one pattern that we have with all this keyhole shape, and we have this space around them. So especially on the head of the keyhole shape, we have a thicker space that is the interprismatic space. Okay, so Of course, the inner part of this enamel can have more scattering of light than the outer part. Okay, it's evident just because of the morphology that it will bounce more the light just because of the shape. Okay, the straight part is more regular. But for me, the important thing again is just that interprismatic space. It's just a blank space, empty space, which is filled with water, especially, and some of organic material too. So those are the canals that can really make the enamel be susceptible to really allow some liquids and some interchange between the outside and the dentin. You know, it's the connection, it's the roads that connect the outside with the dentin. So when we have a lot of water, a lot of interprismatic space, we have a lot of scattering. Okay, the composition here is more water, and then of course that helps to scatter more light. So the young enamel will be more opaque and scattering more light, while the mature enamel is going to suffer a process where the enamel rods are actually going to get thicker. I mean, the interprismatic space is going to get smaller and filled with mineral. And since we don't have so much water anymore and less organic material, then it's more mineral, then material will become more transparent. So it's critical to understand this aging process. Young enamel, it's very opaque, very whitish, okay, while mature enamel is becoming more transparent and more chromatic. Okay, the chroma is more minimal in the enamel. We can reduce it also by bleaching, but the opacity, the content of mineral, we cannot change. So that all will always be the same. So important to understand that. When we have a look at the dentin, we have another perspective here. So the dentin is behaving in a different way. We have the dentinal tubules, which are a structure which is different than the enamel rod, but is especially much bigger. Okay. Dentinal tubules are the ones that really scatter all the light. Okay, it's you can think about them like little cones, elongated, filled with water, and it's actually all this water inside and the organic material inside that actually makes all the scattering of the light. Okay, we have the hydroxyapatite glass in the outside, we have the organic material in the water in the inside, and that's actually the contrast. That's actually what scatters all the light around. So in a young dentin, we have a very, very strong light scattering, light bouncing around these tubules. But on the mature dentin, what's going to happen is we will have a hypermineralization process. So we'll have a sclerotic dentin being formed, and this is just basically the odontoblast retracting inside of a tubule and filling the inside of a tubule with mineral, which is actually hydroxyapatite. So now it's a form of hydroxyapatite that it's a bit more chromatic. It's a bit more yellowish or more orange. And that's actually what makes the dentin more chromatic too. So it's a completely different thing than the young dentin. Now we have a tissue that it's much more mineral and less material, less organic material and water. And it's a huge, huge change in the dentin. Okay, enamel has a subtle change, but dentin has a huge change. So this is the aging process again. The dentin starts being very white, very opaque on a young patient. And as it goes and as it ages, it's becoming more mineralized. So it becomes more chromatic and more translucent at the same time. Again, we've been only focusing on the chroma, only focusing on this part, the lower part, just chroma. But the reality is that this is not really what we need. I mean, only chroma is only part of the equation. Okay, chroma is only part of the equation, but we need to focus more on the opacity, and that is very, very linked to the luminosity of the tooth. Okay, that's why young teeth look very whitish. No, it's not really very whitish. They look very high value. They look with a very bright teeth. Okay, it's not the same white than bright. Okay, you need to disconnect both words because the reality is that it's not the same. Okay. We have the tendency to think that when we just add some white colors, like a translucent white composite, it will just increase the value, but it's not true. Okay, that's not true. We can just have a very dark, very grayish color with a B1 or with a bleach color because it does not have enough brightness. Why? Because it's too translucent material. So remember, young people have very opaque teeth. And that's what we see here. We have teeth and a young person that are very opaque. They can be seen still, even if we look at them with a black background, they look quite high luminosity, high value. But if we transilluminate them, we can see them, they become really dark. And it's only the incisal edge that we can see the translucency there. Okay, so when we see this translucency on the incisal edge, it's very visible. It's very clear that these teeth are really not easy to transilluminate with the light. We need a lot of light to transilluminate them properly. Okay, because this dentin is very opaque. The dentin inside is extremely opaque. But when we look at these teeth that are more chromatic, and we can clearly see this incisal third, which is more grayish, right? All this part has been heavily mineralized, and we tend to think here that of using some gray colors, some gray pigments, but the reality is that we don't need gray here. What we see is just the translucency. It's just that the background is black, so of course there is a transmission of light here. It's becoming really grayish because the incisal third, the whole incisal third, the enamel and the dentin is too translucent, and that's what we see. We see the background through them. If I transilluminate these teeth, we can see immediately it's a completely different story. Now we have a lot of transmission of light. In the previous case, we had very little transmission, only on the incisal, but in these teeth, the incisal part is so translucent that, of course, we have a lot of transmission of light in that incisal third of dentin. So we need to understand that this is all about opacity. Remember, it's not that much about the pigments, it's not that much about the colors, especially when we talk about composite. Composite has a very high capacity to blend regarding color, regarding pigment. Even if our composite is not exactly the same pigment or the same shade as the tooth, it tends to blend very easily when we have the right opacity. If we don't have the right opacity, then it doesn't blend. And of course, we have also this dentin enamel junction layer, which is a boundary between enamel and dentin. It becomes an optical boundary between, right? It's transparent and low refractive index. So in order to analyze all these things, we normally use this dynamic light observation protocol that it's established by the visual synthesis article from Panos and Pascal. And I think it's quite interesting to look at the teeth with all these different lights. Probably, I will say the most critical lights for the patient in their daily life will be the ones on the left. Okay, the ones on the right are very artificial lights that are useful for us, but the reality is that the ones in the left are the ones that the patient can suffer more or less, because every light condition of the patient will always be some sort of combination between reflected light and transillumination. So it's always going to be around here. But the cross-polarized light is what I want to talk about now, because this is a very useful light for us, because we remove, by the use of the filters, of the cross-polarization filters, we remove the specular reflection, and that helps a lot to see better the real color of the tooth, to understand the right color. Okay, this is what we need, because the way our brain sees the color is very limited. It means that when I'm looking at this picture, I tend to think that I can look at the real color of the tooth in these areas where I have no specular reflection. But the reality is that my brain cannot see just that area of the tooth. My brain can only see the whole picture at the same time, which means that it will become really cheat by all these highlights of the flash here. Okay, I cannot see the right colors because of the high contrast produced by the flash. This is the same thing that happens with the Edward Adelson checkerboard. We look at case A and case B, and they look completely different. But if I take a little piece here of the same color as A and I move it in between, you can instantly see that they are exactly the same color. So they look different, but the reality is they are the same. This is the problem of the brain not being capable of resolving properly the color measurement in this scene. Okay, our brain cannot see the just one patch of color, can only see the whole image at the same time. and that's why we have these issues. Also, it happens with these diamond shapes. We have a gradient from a darker gray in the top to a lighter gray in the bottom. We have these whiter colors here, brighter, and we have these darker colors in the bottom, right? But it's not true. The reality is that all these diamond shapes are exactly the same. So all the contrast is just a problem of how to resolve the color in our brain. If I change this to any other row, I can see that it matches perfectly any row. I can put it back into this place and it's still matching. So they are all the same. This is another optical trick, but it's because our limitation and the way we see colors with our brain. So all these areas around the specular, they are perceived as a more dark color instantly just because of these highlights, because the highlights are too strong. The rest of the tooth looks darker. So that's one of the effects when we apply the polarize. We can immediately see that the tooth looks actually much brighter. And this is the reality, because we don't have the specular now to really contaminate our measurements. So now if we'll have a look at this teeth from Pana's article, we can see that the layering, it's going to be quite different from what we've been used to. Normally, we do the layering technique starting from the cervical towards the incisal, and we start with more chromatic colors in the depth in the inside here in the cervical, and as we go to the incisal, we use more whitish colors, we use more bright colors. But the reality is that if we look at these teeth without the enamel, we will see a completely opposite situation. Actually, the incisal third, where the mamelons are, is not white, it's actually the opposite. This is very chromatic and very translucent. This is purely sclerotic dentin. And we need to understand that this is how the aging process works in a normal way. So the mineralization starts from the outside and it goes towards the inside of the tooth, okay? It's never like starting in the inside and going to the outside, right? It doesn't make any sense. In order to the sclerotic dentin to be formed, the odontoblast needs to be retracting the process inside of a tubule and filling slowly the inside of a tubule with a mineral from the outside to the inside. And this process will always start in the areas that are more active, the areas that have more exposure, tension to forces, reaction to forces. The dentin hypermineralized in the incisal edge, in the palatal side. That's where we start with all the sclerotic dentin formation. But the rest of the tooth stays much younger. So actually the cervical third very often is the youngest part that we can find in a natural tooth. And this is quite surprising because it's actually going completely opposite to the layering techniques that we've been using so far. So we've done a lot of analysis of natural teeth and not extracted teeth, but real natural teeth in the mouth of the patients in order to understand this kind of things. And we developed this Penta-laminar concept, which is basically a layering concept that tries to mimic all the different substrates that we can find in tooth. From the outside to the inside, we can find these two areas of enamel, the outer part, which is more straight, the inner part with the bendings of the rod, which is a bit more opaque than the outer part, the dentin enamel complex, very transparent, and a low refractive index boundary. And then the dentin with two different opacities, because we have this sclerotic dentin area and the normal dentin area. So this model, which maybe you can find in some publications in the past, something not exactly as this, but maybe more similar. But the reality is that this is completely different in the way we apply it, because we need to adapt this to also the age of the patient, as we will see in a moment. And this is a concept, which means that it can be simplified. If I analyze the difference between the outer and the inner enamel, it's not very strong. So we may be able to just use only one enamel to copy this, okay? And we can avoid using two enamels. The DC layer, it's technically sensitive, it's difficult to mimic. So very often, if we can do something to avoid doing this very thin layer that is complicated to apply, then it will be more simple for us. So in order to do that, we need to use different composition for enamel and dentin. Then we need to use the two dentins, and here we cannot simplify, okay? If we have a small fracture line, let's say around here, then of course with the small cavities, very often we can only use one dentin. for restoring our class 4. But if we have a longer fracture or a bigger cavity, very often we will need to use 2 dentins. So just keep that in mind. Big cavity, 2 dentins, small cavity, 1 dentin. And then we need to understand this is a dynamic shade concept, which means that the layering pattern we see here is completely different from this teeth if we look at them, let's say 30 years ago, okay? 30 years before extraction, they will probably not have all this sclerotic dentin in the incisal. And this young dentin that we can look at it here, it will be going all the way down towards the incisal edge. So that's why we need to define these aging steps. Okay, from a junior patient to a senior patient, we need to adapt our layering in order to make it more natural. Okay, we cannot do the same layering technique for a young patient than from an older patient. A young patient is actually not very complicated regarding colors, because basically what we need to do is use a very opaque, very white color as a base dentin, and that's it. Then it's just about doing some opalescent enamel. And the tricky part probably in this junior stage is more about the shape, the real shape of the dentin, the real shape of the enamel, having a nice anatomy. This is more difficult in these cases than actually choosing the shades. The only problem is very often we don't have this very opaque shades available, and that's what limits us and what creates the issues of the grayish lines and grayish fractal lines and dark low value restorations. But if you have enough opacity, that's not an issue. So the young stage, now we have a bit of incisal third mineralization, so we have a bit more chroma in the incisal third. And then on the adult stage, we have until the middle third, so it keeps growing. It's just going from the outside to the inside. You can see it clearly. The sclerotic dentin is growing inside, okay? It's especially from the incisal part and from the palatal side. And finally, the senior stage, where we only can see just a little bit of remnants of dentin here, of the opaque dentin, of the young tissues in the cervical area. The rest of the tooth has been completely mineralized already, and it's very grayish. It's not grayish because we have gray pigments, it's grayish because it's too transparent and we see the background underneath. So this is the end, and this is the normal aging process. The reality is that very often we have altered situations where we don't have a normal aging process. We have some fractions, some cervical exposure, some other areas exposed that actually become more sclerotic and more chromatic. And of course, this is a big source of sclerotic dentin formation because we have exposure of the dentin, a big aggression. And then we have chroma in the incisal, chroma in the cervical, and then a white band in between. In the long term, this becomes really more uniform, and we have a very, very uniform color here of the tooth. We have some desaturation produced by the enamel on the sides of the tooth. This is normal, of course. The increased thickness of the enamel is producing this. And also we have this chroma stain in the incisal edge produced by cigarettes. This typical orange color is just the filter of the cigarettes that stains the tooth in this color. But the reality is that this kind of teeth with long-term cervical exposures of fractions and really not a normal aging pattern, because at the end of the day, this is a pathologic aging pattern, had been used as a model of layering, right? So all the layering techniques have the origin on the ceramists observing extracted teeth. Okay, those ceramists were really trying to find out how the tooth is really built from the inside. So they cut teeth, they try to use these extracted teeth in order to learn more from nature. The only problem is that you are not learning from a normal nature, because all these extracted teeth, most of the time they are extracted because they have pathologies. They have maybe fractions, erosions, they have caries, or they have some other disease. And of course, this means it's not a normal aging pattern that we can find them there. You know, it's like it's a bit weird, but it's a kind of that our model of layering, it's a bit more like a zombie, right? We are not using a normal person. We are using someone like with problems, with a deteriorated situation, with decay, with this is not a normal model. This is a pathologic model. So we cannot take this as a reference for making new teeth for our patients, right? This shouldn't be our model for layering, because that becomes really a weird situation where we are mimicking things that are only happening on pathologic teeth, but we are trying to put new smiles and new younger teeth on our patients. So it's actually not really working to get this kind of effects.